Okay, welcome back everybody. You've made it. It's the last video, last part of the last section of the book. Proud of everyone for making it this far. We're just going to cover two examples of using the Galerkin method and then we're done. With that said though, I've got the first example up. However, I do want to jump back to kind of this whole method of mean weighted residuals because this is what we're going to be employing the entire day today. And we're going to just recover what the steps are really quick. So what we always are going to do, and this, you can apply this to the Galerkin method, so just pretend like I'm saying this is the Galerkin method instead. What we're going to do is we start with our PDE, and we need the boundary value to be 0. And then we're going to find finitely many linearly independent functions which satisfy that boundary value, 0 on the boundary. And we're not really going to worry about that definition of naturally adapted. I mean, it's super vague, so we're not really going to worry about that. We'll just pretend like we know what a good collection of functions is. And then we're going to set up this finite sum. In a lot of cases in the real world, it doesn't look like this. It does not look like J and J. It's going to be some finite sum where however many variables we have at the start of our sum is kind of the total number of dimension that our space exists in. And then maybe this will be 5, maybe it'll be 50, maybe it'll be 500. We're just going to cap, the number of terms in the sum at a finite number. And we'll have something like C, N, comma, M as the coefficients that are unknowns. And then we'll know whatever these E sub j's actually look like. So maybe these will look like x to the n, y to the m, right? So these would be like the monomials. This would basically be a Taylor series centered at 0. Basically asking the question, in Galerkin land, what is the best Taylor series centered at 0 that can approximate my PDE? But it might not be x to the n, y to the m, right? We could have something like e to the I n x, e to the I m y. What do you know? That looks like a Fourier series, right? In that case, it's supposed to be more useful to go from -5 to +5, but all of a sudden now you're using a Fourier series to approximate the solution to the PDE. But you could certainly imagine situations between all of those, right? We could jump back to sine nx, cosine my, or something like that, and you're going to have as many terms in this series as you have dimensions, and the n's and the m's are going to be integers, and the x and the y are going to be, the arguments of your function, which try to solve the PDE. So you can have all sorts of these sorts of situations at step 2 where you construct that finite sum. And then in step 3, you're going to plug that finite sum into the PDE itself, right? So all of those finite sums are going in. You don't have to worry about this boundary. It's going to be met for free because you assumed that your basis function satisfied the boundary. But you're really going to be kind of constructing this object f, right? So you want your original PDE to be equal to 0, right? There's that equal to 0 on the right-hand side. So if there was anything on the right-hand side originally, make sure you pull it over to the left-hand side when you construct capital F. And then kind of the important thing is that you're constructing all of these weighted residuals. And in the Galerkin method, these w's are going to be the e's, the basis functions that you're using in the first place. And so you're going to construct as many of these residuals as you have basis functions, and then you're going to solve that system for, those residuals equal to 0, solve that system for these coefficients, which will be the ones that were originally in this sum. Right, you're going to find these coefficients when you solve this system of equations equals 0. You'll find those coefficients. That'll let you reconstruct your function. So that's what we're going to do here. And in the first case, we're going to do it with this basically modified Laplace's equation. There's Laplace's, or I use Poisson's equation. There's Poisson's going on with, if you had those equal to 5, that would be Poisson's, but we've got this modification of phi squared sitting around, so that's making it nonlinear, which makes your life a little bit tricky. And even trickier than that, we've got ourselves some non-zero boundaries. So we do want to be careful when we're trying to use the Galerkin method. If we have non-zero boundaries, there's a reason why I introduced boundary zeroing to you in the last video. So we're going to have to go through some boundary zeroing here. Now I do want to comment, technically I've presented you with the family of functions that I want you to use to approximate the solution here without kind of pre-boundary zeroing. What you're going to have to do is modify this family when you go through your boundary zeroing. So long story short, there's a phi here. That's going to be our boundary zeroing phi. That's going to lob those off for us. We're going to need to subtract phi from f, so we're going to lob that xy off too. So in reality, these are going to end up being our Galerkin basis, even though I started with the xy out front. Okay, so the xy is going to be superfluous. We're going to include it back in at the end, but our Galerkin basis will be these signs, right? Those are kind of going to be the ones that satisfy 0 on the boundary for us. Toward that end, let's actually go through this boundary zeroing process to figure out what the function we're actually going to be analyzing in Galerkin form will be. So to do that, you'll recall what I need to do is I need to find a function, a smooth function that satisfies these boundaries. And like I kind of already said, it's been hinted at pretty strongly. The function that's going to pull that off for us is x times y. So as a smooth function that satisfies the boundaries, in step 2 of boundary zeroing, we then reconstruct the PDE, but I've replaced every phi in the PDE now with psi plus phi, where this latter phi is xy. So all three of these phis are going to be xy. And thankfully now my boundary values are 0. If I want to make that first row of the PD a little bit more explicit, I can actually replace xy in there. So go ahead and replace xy in there, and I act that second derivative in x and y and foil everything out. Thankfully 2 derivatives in x is gone, 2 derivatives in y is gone. Foiling is going to play some games. It's going to give me 2xy psi and x squared y squared. So that's actually going to be my zeroed PDE that results from boundary zeroing, and this is the PDE Galerkin can tell me about. Okay, so now I found this PDE that Galerkin can tell me about because the boundary values were 0 here. Let's keep in mind this 5 should probably be brought to the left-hand side just so that I can have it in the whole form of, capital F is all of this junk, along with a negative 5 equals 0. So that's going to be the PDE Galerkin can tell me about. So what I'm going to do is try to approximate this solution using the Galerkin method. And instead of using that original set of functions I had, I'm going to subtract off this phi of xy, which was xy. So now my actual set of basis functions will be sine pi nx sine pi my. And if we recall back at the beginning, I didn't make this too explicit. I said let's approximate this to 2 terms. So nm equals 1 to 2. So we're going to approximate this up to 2 terms, which means my approximate solution to the zeroed PDE will be a sum from 1 to 2 of CNM, ENM, or ENM. It's given right here. That's equivalently sum from 1 to 2 of CNM sine n pi x sine m pi y. So this is really the function space I want the quote-unquote best approximation in. So I'm finding the best approximation in terms of C and M, right? Those are the only 2 terms that aren't defined for me. There are 4 of them, only 4 terms that aren't well defined already. Everybody knows what sine pi nx and sine pi y are, but I have a choice over these constants, these coefficients. So I'm going to be looking for those coefficients. Well, there's going to be a total of 4 of them, right? Because I have 2 choices for n and 2 choices for m. So a total of 4 coefficients I'm going to be looking for. And I'm going to find them by constructing my system of equations, which are coming from these residuals. So what I need to do is find this capital F, right? So capital F of my approximation, which is capital F of that sum, so we'll be finding an approximation there. That's going to be just me evaluating the entire PDE on phi tilde, or psi tilde, I guess in this case, on psi tilde. So to do that, I'm going to want to know what partial squared x is on psi tilde. Okay, go ahead and calculate that. You're going to get a pi squared n squared from 2 rounds of a chain rule on sine pi and x. To calculate partial y squared on tilde psi, you're going to get pi squared m squared from 2 rounds of a chain rule on sine pi my. And then you'll get some negative signs too. So that's what those 2 terms turn into. That's what I've got going on there and there. And then this psi tilde squared, I'm just grabbing the entire sum and I'm squaring it. And then this psi tilde, I'm grabbing the entire sum, multiplying it by its 2xy. And then my leftover is my x squared y here and my 5. So x squared y and 5. So that's what I'm going to be left with if I plug everything into my PDE, giant little function there. Let's pull 5 to the left-hand side. So let's call it a minus 5 equals 0, where now everything except that 0 really is this capital F that I'm going to be able to construct my residuals from. So that's capital F for residuals. So now that I've found that capital F, I can actually construct these residuals via the Galerkin method. And if we recall what that is, you just integrate over the space, the domain. Let's jump back up to the original problem and figure out what my domain is. Lovely. That's not right. The original domain is this 0, 1 to 0, 1, right? So it's square 0, 1 squared. So my original domain was this space 0, 1 to 0, 1. I'm going to integrate over that space. Dx, dy. And let's just write it out explicitly. How was it defined originally? It's just f against e sub k dvx, right? So my function, capital F, that's all of this stuff that I just calculated. The e sub k, these are my basis elements, right? And my basis elements here were the signs. And then my volume form is the same it always is in 2 dimensions. It's dx dy. So that's me integrating everything correctly and getting my residuals. But that looks pretty ugly. We should actually write these all out so you can, there needs to be a total of 4 of these. There are 4 of these. Right, because I have this for a given k or L in 0 to 1. And so you let k be, or 1 to 2, you let k be 1, L be 1, and then compute this entire thing. You're going to get one answer. You let k be 2, L be 1. You're going to get another answer. You let k be 1, L be 2, you'll get another answer. And you let k be 2, L be 2, you get another answer. So that's a total of 4 of these that we can construct. And if we do construct the 4 of them, that's really what's going on here, equal to 0. Right, everything to the left is just what I covered. But it's really that equal to 0 is going to be a system of 4 equations and 4 unknowns. Where are my unknowns? They're hiding, right? It's CNM, 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 and so on. Because I have a 1 and a 2 there, a 1 and a 2 there, 1 and a 2 there, and so on. There's going to be 4 CNMs sitting around on each one of these equations. If we actually set up the system of 4 equations, 4 unknowns, we solve it, right? They're all equal to 0. Every single one of them is equal to 0. We say we're going to solve for CNM, and what we end up with is negative 0.408, negative 0.001, negative 0.001, and 0.001. Now, those latter 3 seem like really small numbers. They are small, but they're not insubstantially small, so we keep them around. And what we do, now that we found these C's, right, we found 4 C's, we're just going to write out psi approx in xy. It's this sum. It's the sum CNM sine n pi x sine m pi y. N m equals 1 to 2. Well, what is that? It's just c 1 1 sine 1 pi x sine 1 pi y plus c 1 2 sine 1 pi x sine 2 pi y, c 2 1 sine 2 pi x sine 1 pi y, and c 2 2 sine 2 pi x sine 2 pi y. So we have 4 terms in our sum. We've just found 4 coefficients. You just plug each one of them in. That one goes there. That one goes, what is that? That's 1, 2. That one goes there. This one goes here. And this one goes here. And so you just get a collection of 4 sine functions that you're going to add together. There I've made it explicit what they look like. Just add those 4 sine functions together. And we're not quite done, right? Because this solved for psi. So we're done with the Galerkin part. That's solving for psi on the Galerkin part. But let's just recall what our original PDE was this PDE where we weren't able to use Galerkin because of those 2 terms. So the PDE said you can't use Galerkin because of those 2. So what did we do is we went with boundary zeroing and we ended up with this PDE. So Galerkin solved that PDE for me, but not the original PDE. To find the original PDE, if we go back to our boundary zeroing proposition, the original PDE is the boundary zeroed solution, which we approximated with Galerkin methods, plus that one extra term that meets all the boundary conditions for us. So we're going to take our Galerkin approximation, and we're going to add, so there's the Galerkin approximation, we're going to add that term that gave us non-trivial boundary terms. That was xy. When we do that, we actually get an overall approximation. And our overall approximation, if we plot it here in the cyan versus the gray, you can see it's really barely off. You know, there's kind of a spot right here. We can see the gray to the left-hand side, cyan to the right, and they do differ by just a little bit, but it's pretty darn close. And this is at 4 Galerkin terms, right? So I didn't even use that many terms. Like in the finite difference methods, I was using 9 interpolating terms. It's only 4 terms, and we're already getting a really, really nice approximation. Basically globally, right? Globally in the sense of it's meeting everything kind of everywhere all at once. Moving on to the very last example of the book, we're going to just do one more nonlinear problem because these are kind of the ones that nothing else knows how to tackle. So we'll do one more nonlinear problem. And the domain of this problem is all of R2. So we do want to think about what it means to have a boundary condition set to 0 in R2. That's usually showing up as this integrability condition. So that's what I've got here instead of a boundary condition, is our integrability condition, where we're integrating over the whole space and we take phi and we square it, and we want that to stay finite. And this is actually really important in Galerkin methods. I'll scroll down a little bit because at the end of the day, right, these weighted residuals are constructed by integrating over all of space. And so it would be really nice to make sure that, the functions that we're considering are actually integrable over all of space. So it's pretty important to include those if you're ever going to try really anything over an infinite domain, to have this sort of integrability condition sitting around. We do have a nonlinear problem here, so let's see how we can maybe try to solve that using the Galerkin method. And the linear independent set of basis functions I'm going to grab looks like the following. What's actually going on here is these are the monomials. So nothing too special about that. You would think like, okay, it's just like a Taylor series, right? C and M, it's x to the n, y to the m. But we need these to satisfy our boundary conditions. So that's equivalent to saying it either decays out at infinity, because you can't have a finite integral without decay, or that in fact the integral is finite. And so we've multiplied ourselves by a Gaussian to make sure that this is true. So by multiplying each of these terms by Gaussian, we actually can verify this integrability condition. Of course, a regular polynomial would not be integrable over all of space. So that's why we've got the Gaussians there as well, to kind of keep us integrable. So this is going to be our linearly independent set. And we're going to go for nm going from 0 to 1 here. Let's just, once again, we'll just have 4 cases, make our lives a little easy so that when I try to expand things, they don't look absolutely insane. So we'll do 4 cases of undetermined coefficients here. And if we go through our step-by-step process with Galerkin, we're basically going to start with this lovely set that I've already introduced to you. Then moving to step 2, we construct a finite sum approximation, right? So this is phi tilde. And if I replace the basis functions with their actual constructions, x to the m, y to the m, what we get is we get that lovely sum for approximate phi, and we're going to plug that in for every phi up here. So all 3 of those phis are going to be replaced with their sum. That happens in step 3. And to calculate these terms, I'm going to calculate them on the sum itself. And what you see when you calculate on the sum itself is a cute little product rule in x along with the exponential. And similarly for y, when we take a derivative, we're going to see a product rule in the y directions along with the exponential. So we get those as the first derivatives, and of course I'm just replacing that term with its derivative, which is me right here. And similarly in y, I'm replacing this term here, so this is ending up right here. And then I have the squared term of phi as well, which I'm just replacing with its finite sum as well. And the right-hand side comes along for the ride. So this really is, especially if I move the right-hand side to the left with a minus sign here, let's put minus sign there equals 0. So aside from that equals 0, that is your capital F, which you're going to use for residuals calculation. So that's showing up in step 3. In step 4, we can actually construct the residuals, and that's because of Galerkin. Never forget, Galerkin, the weights are just your basis functions, and in this case, the basis functions are these monomials with the exponential, with the Gaussian. And so as always, how do the residuals get calculated? R is always the integral over all space, capital F, which is the left-hand side of the PDE, equals 0, and then you multiply that by the basis functions, and then you integrate over your volume. So in this case, capital F is all of this. My basis functions, which we've been using for a bit, are these monomials by the Gaussian. And then we're integrating over all of volume in R2. And so this is how we construct the residuals. Keep in mind, I have 4 unknowns in constants. How many residuals will I have? I'll have 4, because I can let k equal 1 or 0 or 1. I can let L equal 0 or 1. So there's a total of 4 combinations of K and L in the residuals as well. So my system of equations in step 5 is when the residuals are equal to 0, which is when this lovely giant integral that I was just framing is equal to 0 for all choices of K and L, 0 to 1. So that's me putting a 0 in for K, a 0 in for L, or maybe a 1 in for K, a 0 in for L, a 0 in for K, a 1 in for L, or a 1 in for K, and a 1 in for L. Those are my 4 combinations of residuals. And then keep in mind, these are the undetermined coefficients that will need to be solved for. When I have this system of 4 equations, they're all equal to 0, with 4 unknowns, the unknowns being C11, C00, C01, and C10. 4 equations, 4 unknowns. I can solve on a computer. I just have a computer solve all these integrals for me, because there's no way I'm going to do it myself. And we also have the computer solve the C's, and we get 1.008, 0, 0, and negative 0.380. I do want to comment, though, because Notice how there's one term of c's there multiplied by another term of c's there, and then this term of c's is also squared. We really have terms of the form like c0, 0 squared, c1, 0 squared, c0, 1 squared, c1, 1 squared, and all the cross terms are here too. So it really gets quite intense. And so this is an extremely it's not actually an ill-formed system of equations, it's just that it's nonlinear. There are 16 there are 4 c's, but because they're all squared, there's actually 16 real solutions to this system of equations. So this goes back to the fact that it's a nonlinear PDE. The solutions probably aren't unique to the PDE. So all we're getting here is an approximation to maybe one of the solutions of the PDE, and we have to be okay with that. So what I've done is I've selected, one possible case of these 4 c's, and I've presented it against one possible solution to the PDE. If I actually, write everything out in terms of the c's, at the bottom you can see what the approximation to the PDE is, one possible solution. So there you go, there's the 4-dimensional, or the 4-term Galerkin approximation to this particular PDE, I guess this particular solution of the PDE. And keep in mind, these terms here, 1.088 and negative 3.8 or 0.38, those are just coming from these values for c up here of a positive 1.088 and negative 0.38. The other 2 terms are 0, so they're not showing up. These were the terms corresponding to really x to the 0, y to the 0 in that case, and x to the 1, y to the 1 in that case. The cross terms are disappearing. So there you can see just another Galerkin approximation. You can imagine if I added more and more terms, I would get definitely a better approximation along with these gray lines. Right now it's a little bit steep, but that's just because we're only using 4 terms. Anyway, we've made it. This is the end. I do want to send you off in the right direction though. So to that end, if you like chapter 5 more and you decide you want to go to graduate school for mathematics, look for a functional analysis course. That's really what chapter 5 is hinting at. If you like chapter 6 more, look for a numerical methods course, and that's really what chapter 6 is hinting at. So really when you get your PhD and PDEs, like I kind of did, I was kind of PDEs adjacent to my PhD, you have a couple directions to head in. That's really the numerical methods to head in or the functional analysis to head in. I did more functional analysis, but to this day I have to be aware of the numerical methods just because sometimes other colleagues are using them and asking me to have some comments on what they're doing. So I do have to be aware of them, even though in general I would say I'm more of a functional analyst. But either way, I hope you've enjoyed the course. I certainly have, constructing the book and the course for you. And if you ever have a question, reach out in the future. I'd be happy to answer. See you sometime.